Hello, welcome to the Gemstone Senior Thesis Conference. My name is Dr. Kristen Skendall. I'm the Associate Director of the Gemstone Program, and I have the pleasure of working with this wonderful group of students, Team ATTENT. I'd like to thank the team's librarian, Selena McDonald, who's hiding in the back, and the team's mentor, Dr. Tom Castangwe, who is also hiding in the back. I'm going to turn it over to the team who will give their presentation. We will have time at the end for questions. We'll start from our panel of experts who are here in the front. I'll ask you to introduce yourselves at the end. You only have 10 minutes for your questions in this session, and we'll have an hour with the team afterwards. We'll have a few minutes for general questions from the audience. If you haven't already, please silence any cellular devices that you have in you. And with that, I will turn it over to Team ATTENT.
Hi, my name is Fonwa.
I'm Tracy, Charlene, Erin,
Kevin.
And we will be presenting on behalf of Team ATTENT. Our project was the effect of dietary tartrazine on brain dopamine and the behavioral symptoms of attention deficit hyperactivity disorder. A quick overview of our presentation is that I will go through the background, research problem, and research hypotheses. Tracy will go into the rat model, experimental overview, and tartrazine administration. Charlene will go into the behavioral analysis. Erin will give the biochemical analysis, and Kevin will wrap us up with conclusion, future directions, and acknowledgements. Attention deficit hyperactivity disorder, or ADHD, is the most prevalent neurodevelopmental disorder in the United States. It affects approximately 5% of school-aged children. Patients with ADHD display the following behavioral symptoms: impulsivity, hyperactivity, and inattention. Patients also exhibit decreased levels of dopamine and its associated receptors. There are a variety of treatment options available for those who have ADHD. These include behavioral therapy, parental intervention, educational modifications, and pharmacotherapy. All of these only temporarily eliminate or reduce the symptoms of ADHD. Pharmacotherapy is the most common of these treatment options, and some of the common drugs are Ritalin and Adderall, also known as methylphenidate and amphetamine. And the target of these drugs is to increase brain dopamine. However, the issue with pharmacotherapy is that there are a lot of negative side effects that can happen in patients. This includes anxiety, appetite suppression, and even depression. For this reason, patients often seek alternatives. One alternative that they seek is dietary modifications. Dietary modifications are when patients seek to alter their diet and exclude certain processed foods that contain food additives. This is the focus of our research project. Decreased dopamine has been implicated in ADHD. There are regions of the brain that are especially dopamine rich, and these include the striatum, the ventral tegmental area, the substantia nigra, and the nucleus accumbens. These regions are especially important for ADHD dopamine studies. As previously mentioned, our focus was on dietary modifications. Specifically, we looked at a food dye called tartrazine. This food dye is commonly referred to as yellow number 5. It's found in processed foods such as cereals, soft drinks, candy, and sports drinks. When tartrazine is ingested into the body, only about 2% of it is directly absorbed. The rest of it is broken down into smaller metabolites. The main metabolite is sulfonamic acid. One study has found that this causes hyperactivity in rats. Also, other studies have found that food dyes have been linked to childhood hyperactivity and behavioral problems. Because of the controversy that surrounds tartrazine, it's been banned, and the European Parliament has made sanctions to remove it from food production. And then in 2015, Nestle also removed it from their food products. In this image right here, you'll see an image of tartrazine in the powder form. This middle picture shows the molecular formula for tartrazine. And the picture at the end shows another food product that has tartrazine in it. As you can see on the slide, there are a variety of food products that you may recognize. All of these food products contain tartrazine in them. The research problem that we focused on is that traditional ADHD treatments, such as psychostimulants, induce detrimental side effects. For this reason, many patients seek alternatives. Food additives, such as tartrazine, may impact ADHD behavioral symptoms, but the biochemical cause of this is unknown. So we know that there's a decrease in brain dopamine that's been implicated in ADHD patients, and that ADHD patients display the following behavioral symptoms of impulsivity and hyperactivity. What our research aimed to do was find a relationship between tartrazine and the decrease in brain dopamine and the effect that it has on behavioral symptoms. The research question we asked was, how does an increase in dietary tartrazine impact the level of brain dopamine and ADHD behavioral symptoms of impulsivity and hyperactivity? We hypothesized that an increase in dietary tartrazine will cause an increase in the expression of ADHD behavioral symptoms and a decrease in brain dopamine. Now Tracy will discuss the rat model that we used.
To test our research question, we utilized the spontaneously hypertensive rat model, also known as an SHR. The SHR is regularly used to replicate ADHD in a lab setting because the rats display the same symptoms that humans do with ADHD, such as impulsivity, hyperactivity, and inattention. All of our test subjects were male and approximately 4 to 6 weeks of age when we acquired them, making them young adults. Our study was conducted in 3 phases with a total of 40 test subjects, and we split those up into 4 groups. Groups alpha, beta, gamma, and delta. During phase 1, we acclimated the rats and administered tartrazine. All 4 groups went through this phase. During phase 2, we conducted behavioral analysis. Groups beta, gamma, and delta went through this phase. During phase 3, we euthanized the rats and collected their brains for biochemical analysis. And once again, all 4 groups went through this. All 3 phases were conducted in compliance with our group protocols. And now I'll go into some more detail about tartrazine administration. The chemical was administered in the rat's solid food for 30 days. We had 3 experimental subgroups and 1 control group. The control group received no tartrazine. The low dosage group received 0.05%. The medium dosage group received 0.15%, and the high dosage group received 0.45%. Each group had 10 rats in it. Each day when we went into the rat facility, we would change the rats' food, water, and bedding, weigh how much the rats, weigh how much food they had consumed in the past 24 hours, and write all of that data down. Here we have the average body weight for group alpha, and the trends remain the same for all the other groups. And the error bars here show standard error, and they're consistent with all of our figures. The x-axis shows the day of treatment, and the y-axis shows the body weight. And all 4 groups are shown here. We found that there was no statistically significant difference in average body weight between the experimental groups, which allowed us to rule body weight out as a factor. This graph shows average cumulative food intake for group alpha. The x-axis shows the treatment dosage group, and the y-axis shows cumulative food intake. Once again, we found that there was no statistically significant difference in average food intake between the experimental groups, so we were able to rule out food intake and average body weight as factors. So any difference we saw was attributed to tartrazine and not external factors. And now I will pass it on to Charlene for behavioral analysis.
So behavioral plays a very important role in the understanding, treatment, and diagnosis of ADHD. Therefore, we want to see whether tartrazine impacted the behavior of our rats. The first behavioral analysis tested was impulsivity, or the desire to act on a whim. To test impulsivity, we used a T-maze, as seen in this image here. Okay. In the T-maze, the rats begin in this chamber. In this chamber, and when released, they would travel down the arm and choose either the right arm or the left arm. One of the arms contained a large sugar reward, but also a large time delay before they received the sugar reward. The other arm contained a small sugar reward, but no delay before they received the reward, therefore they received instant gratification. If the rats would choose to go down the smaller arm and choose the smaller sugar reward, they were deemed to be more impulsive. Group beta underwent testing beginning on day 26 of treatment for 4 days. However, the rats would jump out of the maze during the trials, and deeming the results to be inconclusive. Due to the time-sensitive nature of our experiment, we decided to abandon impulsivity. The next behavioral trait analyzed was hyperactivity. We used an open field test to look at this. The rats would be placed in a black box and be allowed to roam the box freely for 15 minutes while we recorded their behavior for 4 days. Groups beta, gamma, and delta were placed in the box. However, group beta continued to jump out of this box. We then reanalyzed our experiment procedure and realized that the yellow light in the laboratory room allowed for the rats to see the difference between the black walls of the box and the outside area. Therefore, they could judge the distance and jump out of the box. Rats cannot see red wavelength light, so by changing the room's light to a red light, which we could see, the rats were unable to differentiate the black box from the outside area, so they did not jump out. Therefore, we did get results from gamma and delta trials for us to analyze. To analyze the behavioral analysis, we used vision technology. The technology would track the center of the rats' bodies as they moved around. The average distance was traveled was tracked, and same with the average velocity, and these variables correlated to hyperactivity behavior. We predicted the more tartrazine given to the rats, the more hyperactive they would be, the more distance traveled, and the more velocity traveled. And that is what our results showed. On this graph, on the x-axis, is the percent tartrazine in the diet. And on the y-axis is the average distance moved. Then we divided the rats into the low, control, medium, and high. There was a significant increase in hyperactivity in the distance traveled between the high dosage group and the control. The medium dosage group did have an increase in the distance traveled. However, it was not significantly greater than the control. This could either be due to the small number of rats used, error in the analysis, or there might be a threshold effect, where only the high dosage group received enough tartrazine in their diet for there to be a behavioral effect. Low dosage group unexpectedly demonstrated a low decrease in distance traveled, and we are unsure as to why this occurred besides error. There was an identical trend observed with average velocity. Now Erin will talk about the behavioral analysis.
Human patients with ADHD often exhibit decreased levels of brain dopamine. This is believed to be the cause of ADHD behavioral symptoms such as impulsivity and hyperactivity. For this reason, we wanted to assess whether or not treating our rats with dietary tartrazine would affect their levels of brain dopamine. This was done in phase 3, our biochemical analysis. Following 30 days of tartrazine administration, all 40 rats were euthanized and their brains were harvested. An image of a rat brain is shown on the screen here. While it may appear to be different from a human brain, it contains all of the very same dopamine-rich regions. In order to analyze our brain samples, we sectioned the brains into 4 quadrants. In our study, we did not specifically dissect or analyze any of the dopamine-rich regions of the brain, but we thought that by analyzing certain quadrants of the brain, we might be able to start predicting what regions are most important in dopamine associated with ADHD. Of these 4 regions assayed, we only analyzed the right front and left hind regions. While there are many parts of the brain tissue that are important to its function, we wanted to look at dopamine, which is a protein, and other proteins contained in the tissue. For this reason, we subjected our samples to several freeze thaw cycles in order to collect just the cell lysate, or what we refer to as the protein lysate, as depicted in the centrifuge tubes. Once we had collected this lysate, we conducted 2 forms of analysis. The first of these was whole protein quantification, which was accomplished with a Bio-Rad assay. While we were specifically looking at brain dopamine levels, we also wanted to quantify the total protein concentration in each section so that we could normalize these brain dopamine values for our analysis. The second study we conducted was brain dopamine quantification, which we accomplished with an enzyme-linked immunosorbent assay. To go into more detail about these techniques, the first of these was our Bio-Rad protein analysis, which was done to quantify total protein concentration in the protein lysates of the right front and left hind regions of the brain. The Bio-Rad kit came with a series of protein standards, which are specifically calibrated solutions for which the exact protein concentration is known. We took these standards and mixed them with the Bio-Rad reagent, which enabled us to produce a colorimetric product. Colorimetric products are products that absorb light at a certain wavelength, and this characteristic allows us to correlate absorbance to concentration and produce what is called a standard curve. An example of the standard curve is shown on the screen. where along the y-axis, we have the absorbance at 595 nanometers, which is the wavelength of light that our product absorbed at. And along the x-axis, we have protein concentration given in milligrams per milliliter. By correlating the absorbance of the protein standards to their known concentration, we were able to produce a standard curve that correlated these two factors together. This was critical for this assay because in the next step, we took our brain samples, for which we did not know the protein concentration. We mixed them with the very same biorad reagent, once again producing the colorimetric product. We were able to take the absorbance of this product and fit that to our standard curve. An example of how this is done is shown with the red dot depicted on the graph. By fitting the data point to our curve, we were then able to correlate the absorbance of our unknown sample to its concentration of protein, thus enabling us to quantify total protein concentration in all of our lysate samples. The next assay we conducted was an enzyme-linked immunosorbent assay, or ELISA. ELISA assays are immunological-based assays that utilize something called an antibody, as depicted here in blue. Antibodies are immunological substances that specifically bind certain proteins or other biological substances. In this case, our kit came with antibodies that specifically bound rat dopamine. We would add our protein lysate samples to the wells containing the antibody, and only the brain dopamine, as depicted here in green, would bind the antibody. Any other proteins would be washed away. In the next step of this assay, we added a secondary antibody, as depicted here in orange, to the well. Similar to the primary antibody, the secondary antibody would also bind any rat dopamine that had already been bound to a primary antibody. However, this antibody came with a specialized enzyme attached to it, which is depicted here with a purple star. In the final step of this assay, we added a substrate to each well, and the specialized enzyme that was attached to our antibody enabled us to convert that substrate to a colorimetric product. Similar to our biorad assay, we were able to correlate the absorbance of that colorimetric product to a specific concentration of brain dopamine. In order to conduct our analysis, we had to analyze all 40 rats. Therefore, we had 40 brains to analyze. Of these brains, we assayed 2 regions of the brain, and in order to ensure consistency in our results, we had to use 2 replicates per region. This meant we had a total of 160 test samples. In addition, we had to assay 12 standards to produce a standard curve correlating absorbance to dopamine, and lastly 2 blanks that enabled us to subtract out any background readings that may have occurred. This meant we had a total of 174 samples to analyze, which presented quite a logistical challenge to our assay. So we overcame that utilizing the device we're seeing here in the video. This is an automated assay system that is located at the United States Department of Agriculture Human Food Nutrition Research Facility. When programmed properly, this robotic device is able to completely carry out our ELISA from start to finish. Not only did this significantly reduce the logistical challenge of our assay, it also prevented human error from occurring that may have occurred if we had done this by hand. I will now discuss some of the findings of our study. In order to analyze our data, we split our samples into 2 replicates, group alpha, rats 1 through 20, and groups beta, gamma, and delta, or rats 21 through 40. Again, this was to ensure that we had consistency between replicates. Shown here on the screen are the results for group alpha, or rats 1 through 20. Along the y-axis, we have brain dopamine levels, and along the x-axis, we have our experimental groups, control, low, medium, and high. Here, the dark bars represent the right front region of the brain, and the light bars represent the left hind region of the brain. This initial replicate revealed to us that when tartrazine is administered in the diet, there is a decrease in brain dopamine, which can also be seen on our percent reduction graph, where instead here, the x-axis represents percent reduction in brain dopamine as compared to our control samples. And along the y-axis, we have our tartrazine treatment groups once again. In each tartrazine treatment group, we did see a net decrease in brain dopamine. However, our results displayed that this was not dose-dependent or stepwise. While these initial results were promising, statistical analysis revealed that there were no statistically significant differences in brain dopamine between our control or any experimental group. This is why it was important to complete a replicate trial. because oftentimes results that are not statistically significant can be statistically significant when the sample size is increased. Thus, shown here on the screen now are the results from groups beta, gamma, and delta, or rats 21 through 40. Again, along the y-axis, we have brain dopamine levels, and our experimental groups control low, medium, and high along the x-axis. The dark bars once again represent the right front region of the brain, while the lighter bars represent the left hind region of the brain. Interestingly, this replicate results revealed that there was a net increase in brain dopamine as tartrazine was administered in the diet. This can also be seen in our percent increase graph, where along the x-axis we have the percent increase in dopamine as compared to our control sample, and our experimental groups along the y-axis. Just as an example, to show the right front region of the median group, we saw as high as a 443% increase in brain dopamine, which was quite puzzling to us, because not only did the results of this replicate contradict the results we saw in our first 20 rats, it also contradicted what we expected to see based on the literature. Furthermore, from a scientific point of view, it was quite puzzling to see increases in brain dopamine on the order of 400%. However, statistical analysis of these results revealed that there was a statistically significant difference in brain dopamine between our control and high group. Therefore, we believe that further biochemical analysis is necessary to resolve the inconsistencies we observed in this dataset, and also to clarify the effect that tartrazine has on brain dopamine. Kevin will now discuss the major conclusions and findings of our study.
So going back to our research question, we were interested in investigating whether increasing dietary tartrazine would affect brain dopamine as well as behavioral symptoms of ADHD. And from our experimentation results, we were able to draw several conclusions. First, it was determined that there is no significant effect of tartrazine on body weights or cumulative food intake in our spontaneously hypertensive rats, or SHRs. And as Tracy mentioned earlier, this is important because it means that any changes we observe in brain dopamine or in behavior can be attributed to changes in tartrazine doses. Moving on to behavioral testing, there was an observable effect of tartrazine on hyperactivity. Specifically, we observed that as tartrazine dose increased, hyperactivity increased as well, with significant differences between our control and high dosage groups, suggesting a potential threshold effect. For a biochemical analysis, there is no dose-dependent effect of tartrazine on brain dopamine. And although there were statistically significant differences between our control and high dosage groups here as well, due to the conflicting nature of the results from our two replicates, more testing is necessary to more definitively determine the effects of tartrazine on brain dopamine. So revisiting our hypotheses, we predicted that an increase in dietary tartrazine will cause an increase in expression of ADHD behavioral symptoms and a decrease in brain dopamine. While our behavioral results support our hypothesis, our biochemical results do not. So where do we go from here? Looking ahead to the future, there are a number of different directions we can take to build off of this project. First, we would be interested in repeating our biochemical and behavioral trials with a larger sample size. By increasing our sample size, we would be able to increase our statistical power and potentially reveal statistically significant results that we were not able to see this time. We would also like to utilize more tartrazine doses. From our behavioral results, we observed that there is a potential threshold effect. So by testing a larger number of tartrazine doses, we would be able to look for this threshold and determine exactly where it is. Additionally, Saul mentioned the nucleus accumbens, striatum, substantia nigra, and ventral tegmental area earlier, which are 4 dopamine-rich regions of the brain. And through cryostat sectioning, dissection, and Western blotting, we'd be able to probe these specific regions of the brain for dopamine. Throughout the process, we encountered difficulties with impulsivity testing. So we would like to test impulsivity again, either by using the TMAs or an alternative means of testing impulsivity. And finally, we hope that our project has provided new insight into the effects of diet on ADHD symptoms and will contribute to the ever-growing literature on alternative treatment methods for ADHD, such as dietary modification. There are many people we'd like to thank for their contributions to the project. First and foremost, we'd like to thank our mentor, Dr. Thomas Castangwe, for his guidance. We would also like to thank Alexander Grillo and Zheng Wei, Alan Zhao for their contributions, our librarian, Selena Nichols McDonald, Dr. Erica Glasper, Molly Heyer, and the entire Glasper lab for their help with behavioral analysis, Carrie Henderson in the United States Department of Agriculture for their help with biochemical analysis, Don Jackson in the University of Maryland Central Animal Resources Facility for help with housing of our rats. Our funding sources including Dr. Robert Buchanan, the Gemstone Program, and the University of Maryland College of Agriculture and Natural Resources, the Gemstone staff for their support, our discussants, Dr. Bonnie Dixon, Dr. David Baer, Dr. Ricardo Oneda, Dr. Cassie Thompson, and Dr. Robert Buchanan, and finally our family and friends for their love and support. Are there any questions?
Well done. We now have about 10 minutes of questions from our discussants. You can go down the row at one question each. If you would like to introduce yourself before you ask your question, and then we'll have time for questions from the audience.
Thank you. Congratulations. I'm David Baer with the U.S. Department of Agriculture. I had a question about the biochemical analyses that you did. There's a lot of variability in the results as seen by the large standard error bars. Any thoughts as to what might be contributing to some of that variability? And if you could find those sources of variability and reduce it, you might be able to start to tease out treatment effects.
Okay, so I can comment a bit on how we prepared our samples. During the sectioning process, I think we could have been a little more precise in forming the quadrants of tissue samples, which could have contributed to some of the variation. In terms of the conflicting nature of our two replicates, it should be noted that when we ran this last 20 brains, we encountered some experimental difficulties with the automated system at the USDA. And so there was a time delay from the time the substrate was added to when we could stop that reaction to read the absorbance. We believe that this could have possibly caused the conflicting nature of our results. However, I think that we have to do further testing to resolve what exactly the problem was causing such variation.
Thank you. Hi, I'm Bob Buchanan. And the question I have is, in your literature review, you indicated that at least in human trials and animal trials, when you provide an oral dose of yellow 5, only about 5%, only about 1% of it is absorbed. Do you have any idea, or how would you go about actually measuring the amount of the dose that was absorbed into your rats? And particularly considering that the brain has a barrier for transfer of a lot of compounds into it, how would you determine the actual amount that crossed the blood-brain barrier and got into the brain tissue?
Can you repeat the first part of your question?
In your literature review, you indicated that about 1% of yellow 5 is actually absorbed.
It was actually 2% of it, is it?
Maybe 2%.
So, right, so of that 2% that's directly absorbed, the rest of it that's not is broken down into smaller metabolites, and those are able to cross the blood-brain barrier.
Okay, so do you have any idea which of those metabolites has an active role in this process?
Right, sulfonilic acid is the main metabolite that has an issue.
So how much of that compound actually gets absorbed by the body?
That's a good question.
And then likewise, how much of it crosses the blood-brain barrier into the tissue that you think it's affecting?
Just to follow up on a way we may be able to determine that. The study were based this off of administered sulfonilic acid to the peritoneal of rats and then observe their behavior. However, if we were to directly administer sulfonilic acid to our rats, we could, after a certain time frame, possibly assay their brains either through having to euthanize and extract brain tissue or using something like a dialysis insert to observe concentrations as they actually occur without having to euthanize the rats, which might give us insight into some real-time absorption and crossing of the barrier.
Hi, I'm Bonnie Dixon. Before we ask any chemistry questions, maybe one that's more pertinent to the whole audience, how is it you chose the dosages for, this yellow 5? Just is it relevant to, children's diets?
So we chose our doses based on past literature. So one thing we want to do is match our methodology. So we wanted to administer tartrazine in the rat's feed. So we essentially took the powdered tartrazine and mixed it into their feed and put it in their cages. And so we took a study that occurred in the past that also administered tartrazine that way, and they did dosages of 0.05%, 0.15%, 0.45%, and that study was done in mice, and that corresponds to about 83 mg per kg in the low dosage, 260 mg per kg in the medium dosage, and about 780 mg per kg in the high dosage. Just a comparison, humans are, the adequate intake, or sorry, like the ADI of tartrazine is 7.5 mg per kg, which is in a rat is about 31.25. So those dosages in mice are a little bit higher just because of the different animal models, but in general those dosages in an animal model need to be higher because of the smaller intestinal surface area of the
Hi, I'm Kathy Thompson. My questions pertain to the behavioral tests that you all chose. Why did you pick those particular tests for the impulsivity and hyperactivity? Are those typically used in this kind of context, or where do those tests come from?
So we at first were looking at different hyperactivity tests. Yeah, because it is something that is commonly used in the literature, but our first thought was actually use running wheels. We unfortunately do not have the money to pay for that, as well as the teenage impulsivity test. Our first thought was actually a 5-choice serial reaction test, where a rat had to choose between 5 different levers, and we're trained to only respond to one. That test would have looked at impulsivity and inattentiveness, but unfortunately we didn't have the money to afford an actual setup. So instead we decided to go with the team-based, which was easier for us to build ourselves as well as to administer. And that's why we chose it. They're both also still very relevant in the field, and they're still commonly used to measure both hyperactivity and impulsivity.
Do you think your results might have been different if you'd gone with a different kind of setup?
It's hard to extrapolate because we didn't actually do it, but it seems like in the literature, things have been done with both the 5-choice serial reaction test as well as the impulsivity T-maze, and the results has been similar across the board. So I don't think there would have been a difference between the two.
Hi, I'm Ricardo Armida. I have a question regarding the actually the rats. Do they have lower dopamine or dopamine receptor? You mentioned that both actually could lead to ADHD. Do they have lower than other groups of rats that don't have those behaviors?
So we chose to use a spontaneously hypertensive rat, and we also looked into the Worcester coyote rat and the Sprague Dolly rat, and all 3 rat models are used to emulate ADHD. The reason we chose this one, it was studied before compared to Worcester coyote, and they determined that the SHR rat, I believe, has high dopamine reuptake, so that it does express low levels of dopamine, and the Worcester coyote they determined was better to emulate non-ADHD patients, actually. So that's why we kind of went with that one.
Thank you. We do have some time for questions from our audience or from the Teams mentor and librarian, if anyone has any questions.
Mike, first of all, say excellent job in getting those to come out. People in first year, but they're our professors, so we didn't tell us. One thing is, you spoke that in your results you found dopamine was decreased in some of the results we used. Okay, so in your results, you found that dopamine was increased. In some of your findings, it was decreased in others, correct? So the thing with dopamine is that also elevated levels of dopamine is involved in schizophrenia, as well as decreased levels of Parkinson's. So do you guys notice any behavioral changes in that aspect? Do you ever feel that your rats were a little psychotic or actually had movement problems in that, or did you not focus on that to so much of an extent? Or was it hard to differentiate if your rat was acting psychotic, did you assume maybe that was just ADHD effects?
Well, since we weren't actually looking for behaviors of psychosis, I don't think we are necessarily knowledgeable enough to say that these symptoms are psychotic, but we did see that rats were a little jumpy, but we just attributed that to hyperactivity.
And when dopamine levels were low, what did you see in regards to that? Was it also, they seemed jumpy, or was it they seemed less emotion, less movement? Was it?
We also looked at our rats, our first round of rats, we were feeding them at an earlier time of the day when they were sleepier, and later for our second round of rats, we looked at them later at night when they were more active. So it's hard for us to compare the behaviors between the two of them because we just noticed them at different times of the day.
Can I ask one more question? That's all right. In regards to ADHD diagnosis, it must be diagnosed before the age of 12 in 2 or more settings. So when you guys were checking your rats, do you feel that maybe some of the rats, if they were older, based on brain maturity, do you think that would have made a difference, or do you think, based on past studies?
So the reason that we chose to get our rats at 4 to 6 weeks is because they are spontaneously hypertensive, and that means that they do develop symptoms of hypertension the older that they are. The ADHD symptoms do persist throughout their age, but the hypertensive does become more of an issue the older that they are. So we chose this rat because although it does have other issues that you need to consider, those don't happen until much later on, which is why we got them at such a young age.
Thank you.
Other questions from the audience?
First, I'd like to just congratulate the school. 4 years, you all have worked hard, you all secured the funding, and you all stuck with the research. I believe some of you have got bitten by those rats, and even though the results were statistically inconclusive, would you say that it has affected any of your choices in your diets? Right now with yellow pie, anyone has gone home and told their families, we need to cut this out?
So I might be like the best person to talk about consuming yellow pie because I had like a lot of Mountain Dew in my first 2 years of college. So I pretty much was taking yellow pie all the time. When the project kind of first came to fruition, I don't think it necessarily changed my mind much, but I guess as we progressed throughout the process and we got some of the results and we started seeing some trends potentially, maybe it started clicking in my mind that I should not be having so much yellow pie, so I'm going to cut that back personally, but yeah, it's affected me a little bit, but it hasn't driven me crazy or anything, so yeah.
Another question?
First of all, good job, guys. My question has 2 parts to it. The first is, why did you choose yellow dye? And checking out the impacts that it has on ADHD. And are there any other dyes that you would have liked to look into, or any dyes that you had searched in during your research that you would have wanted to test out as well?
So currently, there are 9 synthetic food dyes that are approved for use in foods. One of those 9 food dyes is yellow 5, and all these compounds have they're synthetic, so they don't have, their chemical structure is not something that our body's used to. So that's why that group of food colorings was of interest to us. Also, we chose yellow 5 because it was already banned in the European Union. So that was also something controversial in the United States that we wanted to look into. And also there was a history of the sulfonylic acid already affecting the body. And so we wanted to kind of take that a step backward and say, what does yellow 5 do?
Another question? Let's give another round of applause for